Welcome back. If you're watching this, it means that we're at the end of the semester and we're just getting ready for the final exam. And that's all I want to accomplish in this lecture. I just want to practice, practice, practice. I'm not going to introduce any new ideas or concepts. We're just going to practice the type of question that you can expect on that exam. One type of question that you can expect on the exam is this one here. I like this question because it involves a number of different ideas. You have conventional current traveling up a wire, as indicated, and you have an electron flying away from that wire with a certain velocity. And you're asked, what direction is the force on that electron? Well, clearly it's a magnetic force that we're talking about. That wire creates a magnetic field, and that magnetic field pushes on the moving charge. And that makes it a two-step problem. It's like a two-step dance. You first of all have to figure out the field that is pushing on the electron. And to do that, we remember that whenever we have current traveling in a straight line along a wire, we use the straight part of our right hand, our thumb, to represent that conventional current. We know that the B field lines, the magnetic field, make circles around that straight wire. But we can never remember which way those circles rotate. Okay? And that's what we use our right hand for in right hand rule number 2. We use the straight part of our hand to represent the current. The curved part of our hand represents the direction in which that magnetic field goes around the wire. Now you'll notice that with my thumb up, my fingers are pointing away from you over on the right-hand side of the wire and towards you on the left-hand side. So it would be into the board here and out of the board there. Now I don't care about both of those facts. I only care about what the magnetic field looks like over here, where it's affecting the electron, where it's pushing. Okay? And over there, it's away from you or into the page. Now once I have that magnetic field, that's the first step of our two-step problem. The second step is to figure out how that magnetic field is going to push on that traveling charge. And the only right-hand rule that tells us about a magnetic force is right-hand rule number 1. And you remember with right-hand rule number 1, you reach in the direction of the motion. And then, this is the important part, you turn your wrist so that you can wave your fingers of your right hand in the direction of the B field. That forces your thumb in the direction of the magnetic force. But it's a magnetic force on a positive charge. If a positive charge were moving to your right in this magnetic field, then the magnetic force would be up. But I remember that electrons are negative. And so that means they're pushed in the opposite direction, and so the magnetic force would be down, down. You can expect a problem that's like that. It might be a proton, might be an electron, might be going towards the wire, might be going away from the wire. You can expect something like that. Now, we just learned last lecture about inductors. And what we learned was that inductors act very much the opposite from capacitors in circuits. Remember, capacitors, you couldn't change the charge in them immediately. It took time to fill them up, and it took time to drain them empty. With an inductor, what can't change instantly is the current through the inductor. The current through the inductor, we have to either ramp up or ramp down. We can't change it instantly. Now in this case, we have an inductor in parallel with a 45 ohm resistor, And that network is in series with a 5 ohm resistor R2. And the whole thing is connected through a switch to a 200 volt battery. Now again, there are only 3 times that we can look at these problems without using fancy mathematics. We always have a part A, which is right after the switch is closed. We then have a B, which is a long time after a switch is closed. And then we have a part C, which is right after switch is opened again. In other words, after the switch has been closed a long, long time, you throw it open, and right after you throw it open, that'll be the 3rd time. Now, before I close the switch, there's nothing going through R1, there's nothing going through R2, there's nothing going through the inductor. When I close the switch, current immediately goes through R1 and R2, but I can't change the current through an inductor instantly. If it was 0 before I close the switch, then right after I close the switch, it's still 0. You got to ramp that current up from 0 to its final value. And that means that inductor is going to act like an open switch. Now you remember back when we were dealing with capacitors, right after we closed the switch, they were acting like a wire. But an inductor acts like an open switch. So it's kind of like the opposite of a capacitor. Okay? Now what that means, if that inductor is acting like an open switch, all the current has to go along this red path. Okay? It can't go here because that's going to be an open switch. Well, that means I've got 45 ohms plus 5 ohms in series, that's 50 ohms. If I use V equals IR with a 200 volt battery, that means what I've got here I've got 200 volts pushing across 50 ohms, and that's going to give me a current of 4 amps. Okay, if I do V equals IR, this is going to be 200 volts equal to current times 50 ohms. This current is going to be 4 amps. And it's going to be up, leaving the positive terminal of the battery. Okay? Now, in this problem that was in your textbook, I can't remember offhand what questions were being asked. Maybe we could ask, what's the voltage across R2? Well, just use V equals IR. If I've got 4 amps going through a 5 ohm resistor, 4 times 5 is 20. I would have 20 volts here. That means I would have 180 volts there, which means I would have 180 volts there. So if I were to redraw this circuit, I would have 20 volts here, 180 volts here, and because these are parallel to each other, I would have 180 volts here. And so that means that this inductor, as an open switch, is also acting like a 180 volt battery that's fighting the current from flowing there. Now, a long time after the switch is closed, if I were to plot the current through the inductor as a function of time, if I close the switch right there, the current through that inductor is going to ramp up to its final value. But if I look a long time after the switch is closed, after I'm up here, there's no change in current. You remember we had a formula for the voltage across an inductor. It was minus L di delta I over delta T. Now, folks, that's going to be on the front page of your exam, but for heaven's sakes, don't use it. Well, don't use it to get actual numbers, unless the number you want is 0. The only time you use this equation is when the change in current through the inductor is 0. That's up here, a long time after the switch has been closed. It's already, in this case it would be 40 amps, 40 amps, 40 amps, 40 amps. The change in current, if it's always 40 amps, is 0, and that means the voltage across the inductor goes to 0. And then the inductor acts like a wire. So a long time after the switch is closed, it acts like a wire, and that means R1 is shorted out. If I have a wire from one side of R1 to the other side, no current's going to choose to go through R1. And so now my circuit looks like this. Now I've got 200 volts pushing current through 5 ohms. Well, if I use V equals IR, that's going to give me a current through the battery of 40 amps. Okay, 40 amps. Now, if I have 40 amps going through this resistor, then that means that the voltage from here to here is going to be 200 volts. This is acting like a wire, so it has 0 volts. This is parallel to a wire, so it has 0 volts, also because no current's going through it. So that's 0 volts, 200 volts. Okay? And those are the things that I could ask for part B. Now let's look at part C. After the switch has been closed a long time, we throw it open. And now, that inductor acts like a battery. Well, how big a battery? Well, the one thing that you can't change instantly in an inductor is the current. Again, if I plot the current through the inductor as a function of time, if I open the switch, I can't just drop down to 0 current. I've got to ramp down slowly. And so that means that right before I open the switch and right after I open the switch, I essentially have about the same amount of current. Well, I found in part B that that amount of current that was coming down through this inductor was 40 amps. And so now that inductor is going to drive that 40 amps around the circuit this way. By opening that switch, R2 is flapping in the breeze. The battery and R2 are no longer part of a complete circuit. The only complete circuit I have is here, and that inductor is going to make sure that the current doesn't change instantly. If there were 40 amps going down through the inductor right before I open the switch, right after I open the switch, there'll still be 40 amps going down through the inductor. Now, how big of a battery does it have to be? Well, if I've got 45 ohms, and my inductor has to send current this way, and it's going to be 40 amps. Well, if it's sending current around clockwise, then this must be a battery that's oriented that way with the positive side of the battery down. And if I want to find the voltage across that inductor, then I'm just going to use V equals IR, where I'm going to treat that as if it's the battery of the circuit. And so this would be the current through the battery, which would be 40 amps, times the resistance of the circuit, which would be 45 ohms. And that's going to give me 1800 volts. And that indicates why these inductors can be dangerous. If I charge things up with the whole circuit with a 200-volt battery, but if I try to open that switch, I can actually generate a voltage that's much larger than 200 volts, 1800 volts. Now, you saw this in class when they tried to disconnect that power supply from the city, and you had hundreds of millions of volts arcing across as they tried to pull that switch. Okay. Let's look at this problem, problem 18. This is very much the same type of problem as we just solved. Again, there's only 3 times that we can talk about without fancy mathematics. So let's talk about those 3 times. Okay. So, right after the switch is closed, again, we start with no current through the inductor, and we can't change that instantly, so there has to still be no current through that inductor right after I close the switch. That means this is going to be acting like an open switch. Okay? If this is an open switch, that means all of the current is going to go around the left branch. Okay? And so if I want the current through the battery, I would just use V equals IR, and this is 200 volts is equal to I times 50 ohms. And that gives me an I of 4 amps. And that would be up through the battery. Okay? The next part of this problem, we look a long time after the switch is closed. And a long time after the switch is closed, the inductor stopped fighting. It acts like a wire. Okay? So, right after the switch is closed, the inductor acts like a wire. A long time after the switch is closed, the inductor... Oh, did you see the mistake? This is going to be like an open switch. Sorry. It's here that it acts like a wire. Okay. Now, if the inductor is acting like a wire, now that means I've got current going around the left and the right branches. And in each branch, I've got 50 ohms. And so now instead of 4 amps, I have 8 amps. Okay, so now what that circuit's going to look like is I'm going to have 8 amps going through the battery up, and then 4 amps are going to go to the left, and 4 amps are going to go to the right. Okay. Now, after the switch has been closed a long time, we open it again. And by opening this switch, we remove the battery from the circuit. And now, that inductor is going to act like a battery. And it's going to drive current around the only loop that it can drive it, just around the outside. And what we're going to get is that green line there. Well, how big of a battery does it act like? Well, that battery, first of all, is driving current around clockwise. Remember, before we opened the switch, we had 4 amps going down this inductor. We can't change that instantly. I still have to have 4 amps going down through that inductor. Well, that 4 amps has to go all the way around. It has to go through R1 and it has to go through R2. So now what we have is the voltage of the inductor has to be enough to drive 4 amps through 100 ohms. That's V equals IR. That's going to be 400 volts. Okay, and it's going to be oriented such that the positive terminal of that make-believe battery is down to drive the conventional current clockwise. Okay? Now, let's look at a couple of problems. This first problem is from your homework. And what you have is a circuit that has both an inductor and a capacitor in it. Okay? So, you know that there's only 3 times we can talk about the same 3 times that we've been talking about. Right after the switch is closed, a long time after the switch is closed, and then we open the switch again. So, right after the switch is closed, the inductor acts like an open switch. The capacitor is empty, so it acts like a wire. Okay, so let's remind ourselves here. The inductor is an open switch, and the capacitor acts like a wire. Well, in this problem, we're asked to rank the bulbs. Okay, so let me just hold off on that there. Let's rank the bulbs here. Well, all the current is going to go through A, and then it's going to go through C, and then it's going to go through D, and back to the battery. None of the current is going to go through B because it's on an incomplete path. This is an open switch. So that means that A is going to be in series with C and D. They each have to be equally bright, which means they have to have the same voltage across them, and it's got to add up to 90 volts. That means this will be 30 volts, 30 volts, and 30 volts. Okay, I'm going to draw that on the board here. So this is 90 volts. A is going to be 30 volts. B is going to be 0 volts. C is going to be 30 volts. And D is going to be 30 volts. Okay? Now, we're also asked in this problem, what's the voltage difference across the inductor? Well, if I want the voltage difference across what's acting like an open switch, look away from the sun. Over here, I have 30 volts and 30 volts. That means from here to here, I have 60 volts. That means I have to have 60 volts from here to here, and there's 0 volts across B. So the inductor is acting like a battery that's fighting the current through that branch, and it's a 60 volt battery. Okay? Now, let's look at part B. A long time after the switch is closed, now the inductor has stopped fighting, and it's acting like a wire. The capacitor, on the other hand, is full, and so it's acting like an open switch. It's blocking any more flow through the capacitor. And so let's write that up here. Or is acting like a wire. The capacitor is acting like an open switch. Okay. Okay. Well, what's going to happen here? Well, all the current that goes through A has to go through B. Now they're in series. C and D are out. They're dark because they're on an incomplete path. And so now if I redraw this circuit, what it looks like this. So now, if this is a 90 volt battery, these two are going to be in series with each other, and they have to have the same number of volts across them. So that's going to be 45 volts, that's going to be 45 volts, and this is going to be 0 volts, and this is going to be 0 volts, which means I'm going to have the voltage across the capacitor will be 45 volts. Okay? Now, again, in this problem, we're asked to find the voltage difference across the inductor. It's acting like a wire, so it has 0 volts. And we're asked to find the charge stored on the capacitor. Well, in this problem, the charge stored on the capacitor is just the capacitance times the voltage across the capacitor. This is 1.5 farads, which is coulombs per volt, times 45 volts, and that's going to be 67.5 coulombs. Okay? Now, in your homework problem, there wasn't a part C. There wasn't a part C. But we're going to include a part C. What if we open that switch again? Well, suddenly, if I open the switch, the battery's not part of the circuit, and bulb A is not part of the circuit. Suddenly, we have A go out instantly. Okay? Now, what can't change? Well, the only part of the circuit that's still intact is, I've got C, I've got D, I've got a capacitor that's charged up to 45 volts, positive on this side, negative on this side. I have an inductor, and I have another bulb B. So, I know that in order, I know the things that can't change instantly is the charge in the capacitor and the current through the inductor. And I know that before I opened that switch, I had current running down through that inductor. Well, how much current was it? Well, it was enough current to make bulb B 45 volts bright. Well, what's got to happen here? If the current through the inductor can't change instantly, that means that current has to wrap around counterclockwise. And if it's big enough to make B 45 volts bright, then it's big enough to make C 45 volts bright and D 45 volts bright. Because they're now in series. Well, what's it going to take to drive that much current around that loop? Well, the voltage drop around that loop is going to be 45 plus 45 plus 45, or 135 volts. Well, that 45 volt battery is not cutting it. So that means that this inductor must be acting like a battery that's also pushing conventional current around counterclockwise. And if I need a total voltage of 135 volts, and this is only giving me 45, that must mean this must be a 90 volt battery, because 90 and 45 is 135. So I'm pushing current counterclockwise. This is pushing with 90, this is pushing with 45, and that's what gives me the 135 volts I need to drop 45 there, 45 there, and 45 there. Again, that wasn't part of the problem, but it could have been. Okay. Now, let's look at this problem here. Again, maybe I'll just not use the overhead there. This is another version of a problem that has an inductor and a capacitor in it. Again, we can only talk about the 3 times A, B, and C. The difference between this problem and the last problem is that it has resistors instead of bulbs. And so we can get some more numbers with it. If we look at part A, right after the switch is closed, the inductor, you can't change the current through an inductor instantly, so it acts like an open switch. The capacitor is empty, so it acts like a wire. It has 0 volts. And now you see that this wire is shorting out R2, and that open switch is forcing all of the current to go through R1. And so all of the current now is going to go through R1. So what this looks like is I'm going to have current going here that's 9 amps. And I got that by just going the voltage across the battery is equal to the current through the battery times the equivalent resistance of the circuit. So this is 180 volts equal to the current through the battery times 20 ohms. That gives me the current through the battery is equal to 9 amps up. Now, we're asked some questions here in the actual problem on your sample exam. The magnitude and direction of the current, if any, through the battery. Let me just, what the heck, well, we'll do this. Okay, so the magnitude and direction of the current is 9 amps up. The magnitude and direction of the current through resistor R2 is 0. Why? Because it's shorted out. The capacitor acts like a wire. And the voltage across the inductor is going to be the full, is equal to the voltage across R1, which is equal to 180 volts. Okay. Now let's go back to the PC. If we look a long time after the switch is closed, now the inductor has stopped fighting and becomes a wire. The capacitor is full and acts like an open switch. So now it's R1 that's shorted out. All of the current goes through the wire, the inductor, and then it goes through R2 because it can't go through the capacitor. And so now the circuit looks like I've got 180 volts pushing current through an equivalent resistance of R2, which is 40 ohms. And that's going to give me, if I use the same reasoning there, now I'm only going to get 4.5 amps. Okay? Now if we go back to the sample exam, the magnitude of the current is going to be 4.5 amps up through the battery. The charge stored on the capacitor, well, that charge is going to be the capacitance times the change in voltage across the capacitance. Well, the inductor is acting like a wire, and that means the full 180 volts has to be across the capacitor. So that's going to be 0.75 coulombs per volt. That's a farad times 180 volts. And that's going to be 135 coulombs. The magnitude and direction of the current through R1 would be 0. It's shorted out. The inductor acts like a wire. Okay? Now, last part. Part C. If I open the switch again, I've got this circuit. The battery's completely out of the circuit now. And now what I have is an inductor parallel to R1, which is 20 ohms. And I've got a capacitor that's charged up that's parallel to R2, which is 40 ohms. Okay. So what do we know? We know that this capacitor can't drain instantly, so if it was 180 volts before I open the switch, it's still 180 volts. And I also know that I had 4.5 amps flowing down through that inductor, and that can't change. So that inductor is going to turn into a battery to drive that current around. Now, if I look at this point right here, the current flowing there has to be the same as the current flowing down through the inductor, or 4.5 amps. And that means I have to have 4.5 amps flowing up through this R1. Well, that means that 4.5 amps must be coming straight across there. Now I also know that this 180 volt capacitor is parallel to this 180 volt, is parallel to this R2. That means I have to have 180 volts across R2. Well, that means I'm going to have 4.5 amps flowing down through R2. Well, if it's flowing down through R2, it's got to flow to the left there, and it's got to flow to the right there. So what I'm going to end up with is two separate current loops. This one going counterclockwise here, driven by this inductor that's not wanting to change its current. And this one, this current loop going clockwise, driven by this discharging capacitor. Okay? And that's the end of that problem. Okay. Let's go back to our PC. Okay, let's look at some problems that aren't circuits with inductors and capacitors. That means I can get rid of this stuff on the board. We got a 30-volt battery connected to three 10-ohm resistors. Two of the R's are in parallel, and this combination is in series with the third. So let's draw that. That's what it looks like. We want the current and voltage drop for each resistor. Now, the first step in solving any of these problems is to find the current through the battery. Okay, I'm going to need a different purple pen. And to find the current through the battery, I need to reduce this circuit to a simpler circuit where I find the equivalent resistance of the circuit. Well, two 10s in parallel are twice as easy as one 10, so those two 10s look like a 5. And that 5 is in series with a 10, so this equivalent resistance is 15 ohms. And I've got 30 volts pushing current through 15 ohms. That means I'm going to have a current here of 2 amps. Okay, maybe I'll use the blue here. That's going to be 2 amps. When those 2 amps come here, they're going to split, and because these two paths are the same, it will split 50-50 with 1 amp going this way and 1 amp going that way. I can find the voltage across each of these resistors by using V equals IR. 1 amp times 10 ohms is going to be 10 volts. 1 amp times 10 ohms is going to be 10 volts. This amp and this amp are going to come back together and be 2 amps. And if I use V equals IR here, I'm going to have 2 amps times 10 ohms, or 20 volts. So you see that any path from one side of the battery to the other adds up to 30 volts. I've got 10 volts plus 20, 30. I've got 10 volts plus 20, that's 30. Okay. If the magnetic field vector is directed north, well, let's pause. North is that way in this room, okay? And a positive particle is moving east. Well, east is that way in this room. What is the direction of the force on the particle? Okay. A little bit dizzy there. Okay. It's passed. So, if we're looking for a magnetic force, we always use right-hand rule number 1. And you remember, we reach in the direction of the motion. In this case, that motion is going east, or towards the back of the room. We're told that the magnetic field vector is directed north. That's towards the open door there. So I reach in the direction towards the back of the room, east. I turn my wrist so that I can wave in the direction north. And my thumb is pointing up towards the ceiling. And that's the direction of the force on a positive charge. And we're told that it is a positive charge. And so the answer would be up. Okay? I think this is the last problem in our review. An electron is moving in a horizontal plane, that means parallel to the floor, in a region with an upward pointing magnetic field. So the B field is always pointing up. Okay? Now viewed from above, in what direction does the electron circulate? We know that when a charged particle tries to go perpendicular to a magnetic field, it ends up spiraling. It makes a circular motion around the field line. Okay? The question is, which way does it rotate? Well, let's say I'm the electron, okay? And I'm traveling in some direction in a magnetic field that's up. Well, by right-hand rule, I would reach in the direction I'm going, and I would wave my hand in the direction of the B field, which would be up, and my thumb's pointing to the right. Well, that's the force on a positive charge. So if I were a positive charge, I would be moving this way. But I'm not a positive charge. I'm an electron. And that means the force is going to be in the opposite direction, and I'm going to be going this way. Now, if I'm looking down on my motion right now from above, if I were a seagull looking for a target, I would see that I was going around in the counterclockwise direction. Okay? And so the answer is counterclockwise. Folks, it's been a wonderful, wonderful semester, and I wish that we could have spent more time in person. I thrive on that. That's why I went into teaching. But it is what it is, and we did our best. So I wish you good luck on the final exam, and please don't hesitate to contact me if I can be of any assistance to you. Goodbye.